Hello, and thanks for joining me today for the next From Around the Field webinar. Today we'll be talking about blood doping in sport. I'm Laura Lewis, and I'm the Director of Science at the US Anti-Doping Agency. I joined USADA in 2020 after nearly 15 years in the Australian High Performance Sport Network, where I was a physiologist at the Australian Institute of Sport, working with many elite athletes in sports such as track and field, cycling, water polo, and soccer. I have a keen research focus in altitude training, as well as hematological changes induced by training and competition, which is what led me to my current research focus on the athlete biological passport. Today's webinar will be centered around a recently published consensus statement commissioned by the American College of Sports Medicine. If you haven't seen it yet, the paper is open access, so I encourage you all to jump online after the webinar and download a copy. The paper is an update to the 1999 position statement, and I can tell you a lot has happened in this space in the last 25 plus years. For example, the World Anti-Doping Agency was formed. Blood doping became a significant problem, and you may be aware of many high-profile public investigations. So think Operation Puerto, the US Postal investigation. But also we got a new test for synthetic EPO, which was introduced in time for the Sydney Olympic Games in 2000 and is now widely used in routine anti-doping testing. So in terms of today's webinar, we'll cover all of this and more with the three main learning objectives being to firstly understand the definition of blood doping and what substances and methods are listed on the WADA prohibited list. We'll also understand the effects of blood doping in terms of human health and performance. And finally, understanding the direct and indirect methods available for detecting blood doping in sport. So let's jump right in. What is doping, and in particular, what is blood doping? Well, the World Anti-Doping Agency, WADA, defines doping as the violation of any one of 11 different anti-doping rules. But the most common of those are the presence or the use of a prohibited substance or method. So WADA prohibits the use of certain drugs and methods based on three criteria. And for something to be considered prohibited, it needs to meet at least two of the following three. The first being the potential to enhance or actually enhance sports performance. Second, the substance or method represents an actual or potential risk to health. And third, the substance or method violates the spirit of sport. And that's defined by WADA as a celebration of the human spirit, body and mind. And this really is a catch-all criteria, really revolving around fairness in case one of the other two criteria hasn't been met. So blood doping is defined as the practice of artificially increasing red blood cell mass using either a prohibited substance or a method, with the goal to enable greater transportation of oxygen to muscles to enhance performance and recovery. As we'll talk about later, blood doping fulfills all three criteria for inclusion on the prohibited list. So blood doping is prohibited at all times under the World Anti-Doping Code, and it appears on the WADA prohibited list in a number of places, both in terms of prohibited substances, so that's the S categories, and prohibited methods, the M categories. So EPO and other agents affecting erythropoiesis, so the production of red blood cells, those are listed under S2. So that's the category for peptide hormones, growth factors, related substances, and mimetics. Then we've got our prohibited methods. So M1 refers to the manipulation of blood and blood components, and this includes the administration or reintroduction of any quantity of autologous, allogenic, so homologous, or heterologous blood or red blood cell products of any origin into the circulatory system. So in other words, taking blood out and reinfusing it at a later date or using donor blood. M1.2 refers to artificially enhancing the uptake, transport or delivery of oxygen, and then 1.3 is any form of intravascular manipulation of the blood or blood components by physical or chemical means. We've also got M3, which focuses on gene and cell doping. And then, although not really blood doping per se, we have M2.2, which refers to intravenous infusions or injections of more than a total of 100 mils per 12 hours, except for those that are legitimately received in the course of hospital treatment, surgical procedures, or clinical diagnostic investigations. So that's really our IV fluid replacement and think IV drips after competition, which are now prohibited. So in terms of the history of blood doping and its detection, it's really pretty interesting, and we could probably fill a whole webinar just on that. But for time, we've included a high-level timeline of key events, both in the paper, but also shown here. So we start in the 1940s, when the first research into blood doping began, but it really wasn't until the 70s and 80s when blood doping drew public attention. So in 1984, the US cycling team revealed that they had infused blood before winning 9 medals at the LA Olympics, and that ended a 72-year drought of medals, and that really prompted the IOC to ban the practice. We then entered a new era of blood doping in the late 1990s, early 2000s, with the production of synthetic EPO. And direct detection not possible until the Sydney Olympic Games. So we really had this EPO epidemic in sport. Still, a number of scandals continued to break into the 2000s, including Operation Puerto, the US postal investigation, Operation Atlas, and these really showed that blood doping was not going away anytime soon. But fortunately, advances in blood collection, transport and analysis really facilitated the introduction of indirect methods such as the Athlete Biological Passport, which provided a new tool in the fight against doping. Okay, so let's move on now to the physiology of blood doping and what is actually happening in the human body. So we've already said it several times, but really to hammer it home, the primary goal of blood transfusions and EPO administration is really to increase the absolute numbers of red cells within the body. And this is most easily quantified in research settings by measuring red blood cell or hemoglobin mass. This is another figure from the paper, and it's a very basic summary of the erythropoietic system. So of course we have the kidneys responding to oxygen sensing and producing endogenous, so natural EPO to stimulate blood cell production in the bone marrow. So our orange boxes in this cycle indicate where within the cycle the different doping agents or methods can exert an effect. So for example, EPO administration will overrule the oxygen sensing control element of the kidneys and directly stimulate erythropoiesis. Whereas blood transfusions occur downstream of the bone marrow and immediately increase hemoglobin mass by infusing directly into the bloodstream. So on the next slide, you'll see, as we just mentioned, that blood transfusion has a clear and immediate effect on hemoglobin mass. We've got some data here from a study where hemoglobin mass was measured after blood was withdrawn and again measured after reinfusion. So when blood is withdrawn, hemoglobin mass falls. We've removed red blood cells. And natural recovery does take time because the body must regenerate those red cells that were lost. But when blood is reintroduced, hemoglobin mass increases. And the magnitude of hemoglobin mass change depends on the volume of the blood that's reinfused. So one standard blood transfusion of packed red blood cells, if that's prepared from 1 unit of whole blood, that contains about 60 grams of hemoglobin mass and will result in about a 6 to 7% increase in an individual possessing about 900 grams of hemoglobin. Administration of erythropoietic stimulating agents, so that's such as synthetic EPO, they also serve to increase hemoglobin mass. But this time it's by accelerating erythropoiesis. So this effect is obviously not as immediate as blood transfusions, as of course the body still needs to produce the red cells. And although we can accelerate the production in terms of the initial stimulation, we can't accelerate the time course of the maturation of the cells. The time course of the increase is also closely related to the dosing regimen, as is the magnitude of the hemoglobin mass response. So more regular and larger doses of EPO will stimulate a greater and faster response. For example, here we have some data showing 4 weeks of weekly EPO injections, and you can see the time course of the hemoglobin mass response, and also that the hemoglobin mass stays elevated for several weeks after because the new red cells that have been produced will stay around in the system for that period of time. So what does all of this do to performance? After all, one of our 3 prohibited list criteria is that it has to enhance performance or at least have the potential to. So, as you know, maximal endurance performance is primarily determined by oxygen delivery to and use by working muscles. So in other words, the Fick principle. So if you think alterations to hemoglobin mass have the potential to significantly alter maximal aerobic capacity by increasing arterial oxygen content, then it would follow that they have the potential to enhance performance. And indeed, there's a really strong relationship that exists between hemoglobin mass and VO2 max. So a change in VO2 max of 4 to 5 mils per minute can be expected for every increase of 1 gram in hemoglobin mass. And remember, I told you that one bag of blood that's infused might be increasing hemoglobin mass by upwards of 60 grams. In addition, marked effects of athletic performance, so that's the ability to complete a defined task or effort to a high standard, they've also been demonstrated in numerous research settings following blood doping techniques, particularly those tasks that are assessing endurance performance, where the ability to sustain a high percentage of your VO2 max is critical to success. There have been a number of studies with cross-country skiers, runners, cyclists, both in terms of time trials or time to exhaustion protocols that have shown dramatic improvements in performance. And in addition to that, it's not only competition performance that can benefit from blood doping, but it's also the training effect that athletes would receive following the doping, which can be augmented. Research has shown maintenance of elevated VO2 max can last long past the life cycle of those infused red blood cells. And this is likely due to the better training that the athletes are able to do in that blood dope state. They may also be able to recover faster and thus endure an increased training load, which then induces further training adaptations from those not subject to blood doping. So when considering the physiological and the performance effects of blood doping, it's also important to acknowledge that accelerated erythropoiesis can also be stimulated by endogenous production of EPO in response to hypoxia. So for this reason, our adaptation to altitude has often been dubbed as like a natural form of blood doping. And so altitude training now routinely features in many training programs of elite athletes all around the world. Here you can see the time course of the erythropoietic response to altitude, which has been well studied. And here we can see that hemoglobin mass increases, in about 3 to 4% over a 4-week period at 3,500 meters. And we're kind of thinking about comparing that to that 3 to 4 week EPO dosing regimen that I showed a few slides earlier. But what's key here is that the magnitude of that change in hemoglobin mass following blood doping or EPO administration, that has the potential to be like almost double what can be expected via the altitude-induced EPO pathway that we typically see when athletes train at altitude. So really, that's to say that the altitude-induced change is far more subtle, and they're related to the overall hypoxic dose. And further, for any given dose, both the natural EPO response and the overall adaptive response in terms of hemoglobin mass increases, they're highly variable between individuals. And while these increases in hemoglobin mass should then lead to increases in VO2 max and performance following the altitude training, they're by no means guaranteed, and they really do appear to be influenced by other factors that can modulate that athlete's ability to adapt to altitude, such as training load, diet, overall health status, and this is really a key reason as to why altitude training is not prohibited in sport, but blood doping is. So we'll now move away from the performance aspect and really think about those health risks associated with blood doping and fulfilling that second criteria of the prohibited list. So the substances and methods that we're talking about that are abused in blood doping, particularly blood transfusions and the drug EPO, they really stem from life-saving medical advancements. However, like any medical intervention, there are side effects and they can certainly be exacerbated if the techniques are abused by healthy individuals in uncontrolled settings. So these risks really, they're broadly placed into two different categories. We've got pharmacological, and these are more associated with specific drug use, and we have known risks such as death, stroke, and thromboembolism. But then we have those that are associated with more procedural risks and really stem from contamination, either during the storage process or reinfusion, or degradation because the blood was not properly stored. And then again, the known risks associated with those are really quite severe. So overall, artificially increasing hemoglobin mass by these blood doping procedures really does carry significant risk of adverse events and should not be used outside of clinical situations. So in terms of prevalence and detection, it's quite difficult to get a handle on how big a problem blood doping is in sport because to measure prevalence we need to look at available sources which include published testimony, athlete data after sanctions, as well as direct surveys. And so we're really relying on athletes to tell the truth, or our alternative is to catch athletes and then have a record of prevalence that way. So in terms of actual detection, anti-doping testing consists of both in and out of competition testing. But the holy grail is really trying to test the right athlete with the right test at the right time. Because of course not every athlete is tested at every competition, and only athletes who meet certain performance criteria are part of an anti-doping organization's registered testing pool, and those are the athletes that are tested out of competition. So in actual fact, the detection rate from testing is quite low. It's less than 1% globally. But through anonymous surveys and analysis of blood data, we get the suggestion that the prevalence might actually be a fair bit higher. So, for example, data from the International Cross-Country Ski Championships suggested that 50% of medal winners had abnormal hematologic profiles. And similarly, an anonymous survey completed in competition by World Athletics estimated the overall prevalence of doping, so all prohibited list categories, not just blood doping, was between 39 and 62%, whereas the prevalence of blood doping in elite track and field athletes using hematological passport data was estimated to be between 15 and 18% between 2011 and 2013. So all of this is to say that the true prevalence remains unknown. In terms of detection, traditional anti-doping testing uses direct methods to detect the presence of a prohibited substance in a sample. For blood doping, this would involve collection of a urine or a blood sample, and then the laboratory will perform specialized analysis for erythropoietic stimulating agents. And this is to differentiate between the endogenous EPO that's naturally produced by the body and synthetic EPO. For direct testing methods, the timing of sample collection is really key since the detection window is fairly short. So that means that the substance is cleared by the body fairly quickly after use. This can be just a matter of days and can be even shorter when microdoses are used. It's also really important to note that there is currently no direct test for autologous blood doping. So that's if someone is to remove their own blood and put it back into their body. We currently do not have a direct test for that. Therefore, in an effort to combat the challenges of direct testing that we just highlighted, indirect testing methods were pioneered by researchers in the early 2000s, and this culminated in the Athlete Biological Passport being introduced in 2009. So the premise of the Athlete Biological Passport, also known as the ABP, is to use biological data to track the effects of doping over time. And in the blood passport, the primary markers that we're concerned with are hemoglobin concentration, reticulocyte percentage, so that's the percentage of young red blood cells that have been produced, and also the OFF score. So the ABP uses Bayesian statistics and plots the samples as they're collected individually for the athlete over time, but also calculates an upper and a lower reference limit for each individual. Samples that exceed the predicted limits, either above or below, are flagged by the model, and then they're reviewed by an independent expert. So the ABP is most powerful when the results are interpreted together. So that means not just looking at one parameter in isolation, but looking at all three in combination. So here, in this study, a doping scheme was recreated in a group of study subjects who are participating in a simulated cycling season. And you can see here that when blood was infused by, is indicated in these graphs by the arrows sort of going upwards, so it's blood going into the system. So when blood was infused, hemoglobin rises, but there's also a down regulation of the reticulocytes in that bottom panel, and together that combines to make a high OFF score, which actually exceeds the upper limit, and in this case would flag within the system to require further review. Similarly, you can see here when blood is removed, as indicated by the arrows coming downwards, you can see a fall in hemoglobin concentration, and this was actually 2 units of blood withdrawn at this time, and this has a resulting effect on a large stimulation of reticulocytes to regenerate red blood cells after that withdrawal, and also a fall in the OFF score. So let's go back to our summary figure of the erythropoietic system, and now we've added in some blue boxes, and these are a summary of the various detection methods that we have available to us. So when synthetic EPOs and other erythropoietic stimulating agents are used, we can do direct testing in urine and blood, as we mentioned. On further downstream on the pathway, after the red blood cells have been made, we then have a number of other methods available to us. We can look, as we've just seen, at the athlete biological passport and the effects of those erythropoietic stimulating agents, but also the effects of infusing or withdrawing blood. We can also use a blood sample here to detect homologous blood tests, homologous blood transfusions. And there are some other emerging methods that are being further investigated, such as the population characteristics of the red blood cells themselves, or one could measure hemoglobin mass or various plasticizers that might be present from storing blood and then reinfusing it at a later stage. So it's clear that existing blood doping techniques have proven to be pretty effective for a fair while now, and it is likely that athletes will continue to try and exploit ways to improve their endurance performance through these methods and other pharmaceutical interventions to increase red blood cell production. So as that threat continues to evolve and new technologies emerge, we're specifically concerned perhaps about the impact of gene doping, particularly related to erythropoiesis-related genes, and how this might be exploited in the future. So it's important then that detection methods continue to evolve and be investigated, but this also comes with challenges. New tests must have a very high specificity. We don't want to get false positives. That's a very high cost of anti-doping testing. Its athletes' careers are on the line, so the tests must be very specific, but then they also have to have good sensitivity, so they need to minimize the number of those false negatives. Ideally, we would have an extended detection window, being able to detect for upwards of a number of days to weeks, and again at the same time being able to detect multiple targets within one sample, or particularly within one type of analysis, for both efficiency within the lab, but also cost efficiencies there. So increasingly for anti-doping organisations, we're having to design really individualised testing programs, and these are based on dynamic risk assessment of several risk factors, with the hope that these have the potential to better determine when and where to effectively conduct athlete testing. So lastly, I just wanted to finish on a topic that was making headlines last summer and was only briefly touched upon in this new paper. Many of you will be very familiar with the carbon monoxide rebreathing method because it's a staple in physiology research, particularly when we're looking at altitude training and other training interventions. So it was really quite surprising to hear reports coming out of the Tour de France in 2024 that athletes were doping with carbon monoxide. And I guess the idea stemmed from a very well-controlled study performed by Walter Schmidt's group, in which subjects were given chronic low-dose carbon monoxide for 3 weeks to simulate a pseudo-altitude environment. Really important here is the study was incredibly well controlled and incredibly safe. But perhaps unsurprisingly, because of this hypoxic environment that they created, hemoglobin mass increased by almost 5%, and again was associated, as one would expect, with positive increases in VO2 max. And remember, these are similar changes that we see with altitude training, but perhaps this could all be done from the comfort of one's home training environment. It's unlikely that the professional cyclists, in my opinion, were doing this, and I think rather many journalists may have been getting confused between a diagnostic test that was being appropriately used by their support staff to measure the effect of various training interventions. I think they were confusing that with doping, but what it did do is it highlighted what a terrible idea this would be as a training intervention amongst athletic populations, not least because it's, of course, potentially fatal if not done properly. So the UCI have since banned the use of carbon monoxide inhalation as a intervention. And it was actually at the start of this year, so as of 1st of January 2026, WADA has also added a new category, M1.4, to the prohibited list, which clearly states that the use for enhancement purposes, the use of CO inhalation is prohibited, but use within appropriate settings as a diagnostic test is still permitted. So to briefly conclude today's webinar, it is the position of the American College of Sports Medicine that any blood doping procedure used to improve athletic performance is unethical and unfair and exposes the athlete to unwarranted and potentially serious health risks. We've seen here clearly that blood doping can enhance an athlete's oxygen carrying capacity through accelerating hemoglobin mass or increasing hemoglobin mass, and in doing so improves an athlete's ability to perform both submaximal and maximal endurance efforts far beyond normal training interventions, and this includes adaptation to hypoxic environments. Since the first ACSM position stand over 25 years ago, the science and technology surrounding erythropoiesis, pharmacological intervention and doping detection has all advanced substantially. So as long as competitive fairness and athlete health and wellness remain fundamental components of sport governance, strong efforts really do need to continue in the areas of doping detection and education of athletes, coaches and medical professions on the risks associated with blood doping so that we can keep sport clean and fair for all. So I'd just like to thank my fellow co-authors on this paper and also the ACSM Evidence-Based Practice Committee for commissioning the statement and organising this webinar. And I think it's now an opportunity for some Q&A before we wrap up. Thanks.